Title of this presentation actually design and construction of high-speed hard chine planing hull for Sri Lankan boating industry. Actually, this was a project done by me when I was on sabbatical leave as a hobby. Actually, I did this, and at this moment, actually, I am presenting it as a technical work. Now, when it comes to this Sri Lankan boat building, actually, we have a very great history because I mean. We have started with a wooden board, and nowadays actually you find a lot of fiberglass board building. And our location, as everybody talk about, our location can be actually good, can be a good place, or can be a place for hub in all aspects, or all areas. So even this board building can become under the maritime hub concept. Now, when it comes to this board building industry, mainly we have this fishing boat building in our country, and in addition we have this leisure as well as pleasure boat and petrol craft as well as fast attack craft and the speed boats. Those basically actually built by the dockyard PLC etc. But here I want to highlight the design and building, and we have copying and building also in our country very much, and especially when it comes to this fiberglass industry because copying and building is very easy because you topple the boat and get the mold, and then you reproduce the same thing. And it's also happening everywhere in the world actually, not even in Sri Lanka. But my interest was really design and building a boat. So I'm talking about design and building. So when it comes to a design of a small boat, especially we can categorize this into a hull shape. Hull shape basically we design for speed, stability, seakeeping and maneuverability. That means how to get the maximum speed with the minimum power. It should be a stable vessel in the sea or in the water at least, in the water. And seakeeping means how it behave in the rough sea or any kind of state of sea, as well as the maneuverability. I mean how we can maneuver the vessel without any problems. So those things should be important aspect looking at the hull shape. And of course the hull strength is another aspect to be discussed, that is mainly for the strength of the hull. And then deck and internal arrangement, basically when it comes to small boats, the appearance is very important, and then safety, comfort and the space allocations. And here when it comes to design, actually we must be knowledgeable about these hull types. Basically, there are three hull types when it comes to the design of a hull shape. It's called displacement and semi-displacement and planing. You can see actually from the figures how it looks like. The normal ship shape is we call as a displacement ship, actually, or displacement hulls. We cannot move at a high speed, and you normally move at a lower speed, that is most economical hulls. But when it comes to a semi-displacement, that is V shape with a round bilge, we use it for medium speed like even 30-40 knots. But planing hulls we usually use for 40-50 knots, or even it can be for 30-25 knots as well. The difference you can see with the planing hull, actually Professor Jatlik was asking me what is the hard chine mean. That is the intersection of the bottom and the side like this with a sharp edge, we call hard chine. And when there is a curvature at the intersection, we call it the soft chine. Now, this is what is important with respect to a speed that a hull can attain. You can see the displacement hull actually are good for low speeds. Now here there is a term actually coming from the crude number we call speed length ratio, that is VO square root of 12, and based on that you can see that 1.34 is the limiting value for a displacement hull, and beyond that you need a lot of power if you want to get that hull to a significant speed, and it's not a useful, it's actually useless because we have to have a lot of power. And then the next category, semi-displacement, actually we can achieve a moderate speed, and then the planing hull, but it's still with a lot of power, you can see. This classification comes actually, or this ranges come based on the thing called hull speed. Actually when wave length is equal to ship length, we get this equation, V equal 1.34 square root of L. That is the limiting value for a displacement hull. Normally ships are well below that speed. Okay, and the semi-displacement hulls usually above that. It has a moderate speeds, or otherwise normally it exceeds this value to some extent. But when it comes to planing hull actually can go at any speed above this value. Planing vessel exceeds the hull speed by overcoming the bow wave. That means this is the one actually constrains the hull to attain a speed. When the hull is moving in the water, there will be a wave generated by the hull, and the bow wave has to be overcome if the hull has to attain a speed. And that is the concept in planing hull, to overcome the bow wave and then attain the speed. So in a planing hull, the total weight actually at zero speed is supported by the hydrostatic lift, or otherwise buoyancy. And when it is moving, what will happen? It will be partly supported by the hydrostatic and then partly supported by the hydrodynamic. As the speed increases, you can see hydrodynamic lift increases, hydrostatic lift decreases, and center of gravity of the vessel also increases at the same time. So you can see this is a 3 stage of planing. Actually the board with 3 pictures. The first picture actually is about to overcome the bow wave. And you can see second one is partly planing, and third one is fully planed. So these are the 3 stages, and with these you can see how the power needed goes up, or otherwise resistance goes up, and then what is the value of VO square root of L in the range. You can see the limiting values here again 1.5 and 2.5 etc. So when it comes to a design of a planing hull, these are the things very important actually when it comes to design consideration. We call LP or BPA. I will show that from a diagram. I think it's clear. That is the length over LP is the length of the chine area, AB is the area of the chine area or projected area of the chine, and then BPA is called as the average breadth corresponding to that. It's given as actually AP over LP. Now these are the factors very important to be considered for the designing. That means LP upon BPA, and then the area upon nabla to the power 2/3 mean is the non-dimensional size weight ratio, and that is very important. And the longitudinal center of gravity location we call LCG location, that is important. And then beta is called dead rise angle. You can see what you mean by dead rise angle, and that is also very important. And then the longitudinal curvature of buttock. That means when you cut the hull longitudinally parallel to the center line, you get the shapes. Here green line indicate those buttock line, and the buttock slope also very important. Otherwise you don't get the lift properly to the hull. Otherwise there won't be planing in the hull if you don't get the proper curvature for the buttock. And then the shape of chine and shape of cross section. Those are important things when it comes to design of planing hull. So these are being actually given here in this diagram. Now dead rise angle also very important. Actually that is depending on your requirement. If the vessel is to be operated in inshore, then your angle should be between 10-12, and if it is coastal 15-20, and if it is high seas or deep seas 20-25. And even practically you can see more than 25 also whenever you need very high speeds. That is to have the cushioning effect when the vessel is moving in rough sea. And dead right variation should provide the necessary angle of attack to produce the dynamic lift. Dynamic lift reduces the wetted surface area as well, and the sharp edge chine at the intersection of the bottom and the side will actually create the hard chine that help to actually separate the water from the side of the vessel. We call actually spray line, and then deep submerged transom that will help again to separate the water from the transom, and also straight buttock lines. So when it comes to hull generation, normally it can be designed on a 3D form. 3D hull generation, and while you do the design, you have to play with it, and you have to understand the shape and whether it has come to a correct, and also then you need to do the changes by looking at it. And then if you look at the hydrostatic, you can see whether you have to change it or not to get the stability. Now these are actually sample views of a 3D design, but I'm not going to explain that 3D modeling here, just the views that you get when you do the design. You can see you get a perspective view. Looking at it, you can actually correct what your design is. And then the particulars coming out of design. I'm not going to show you that detail because I have a little video to show you. And then the power prediction, depending on the LCD, we got the power prediction, and LCD was assumed because it can be changed depending on the construction. But for 3 different LCD values, the power was estimated. Now this is the plug of the board produced. It's out of melamine board before finishing, and actually it has to be finished. It does and has to be finished before you get the mold of it. And this is the deck mold and the deck plug. And this is one complete board with all fittings. This is another one. Actually, this was sold locally to one of the gentlemen here. And then we conduct the speed trial and got the speed measured for power ratings, and we found it's very satisfactory with the predicted power. And I will show you now the video that we recorded during this trial. The red light has not come.
Kalau